Hello everyone. Now we are going to move on to chapter 9 here, and then we go to chapter 10, and then there's a few more chapters, I believe, one or two after that we will cover, and that will be the end of this course. Okay, and then later on, um, I'll talk about what's left in store for the class, but let's resume here talking about the last periodic trend of chapter 8, and then we'll talk about chapter 9 material. Okay, so the last periodic trend that we usually talk about is electron affinity. So this concept is the energy change. So when we talk about chemistry, we're always interested in these energy changes. When a atom gains or loses an electron, or another related process. So electron affinity, or EA, is the opposite process of ionization energy, because in this sense you're losing energy. So basically, it's like forming a bond, right? You gain an electron, you're going to release some energy, and that's going to be a spontaneous result. So it's kind of the opposite of ionization energy. Okay. So the more energy that's released, the higher the electron affinity. So we kind of say, okay, this atom has a high affinity for this electron, and the trends for electron affinity are not clear, but the general trend is it's the same as ionization energy. So the more the more you move to the right of the periodic table, the more energy you release, and that's because as you move across the periodic table in a row, the proton number or atomic number is increasing. So the ability for an electron in the gas phase, an atom, sorry, not electron, in the gas phase, the easier it is to, or the more likely it is for an electron to be added to an atom, because the nucleus has a higher effective charge. Okay. So the thing about these kind of energies, it depends on where the energy goes. So we just finished going over thermochemistry. So it's going to be either negative, positive, or zero. So in this case, negative means energy was released. So it's you get to a lower energy position. The atom or the product that's formed is of lower energy. Okay, so energy is released. It releases energy because it has too much. Okay. Positive means in order to add an electron, you must put energy into it. So that's not a very favorable process. So that will probably happen to like elements like metals. They don't like electrons. So it'll probably happen to maybe metal atoms. Okay. So to produce a negative ion, energy has to be added if it's positive for electron affinity. And then if it's zero, that means this process is neither good nor bad for this transformation, and it's neither favorable or unfavorable. Okay, so let's look at this trend here, and we see here, you see all the metals here. You see the metal atoms, or the noble gases here. They're really low, and we see the non-metals, like things to the right of the periodic table, they're relatively high, right? So, but see, the trend is not exactly clear, because we do see some metals have negative electron affinities, and that could probably be attributed because they're transition metals, and some transition metals, they're what we call electronegative. So they do have some tendency to pull on electrons, and so some tend to be fairly have high ionization energies. Okay, so the trend is not exactly clear, but as we can see here, the halogens tend to have the most. And we see here the halogens here: fluorine, chlorine, bromine, and iodine. They tend to have the highest electron affinities. And We can also think about electron affinities. They're related to electron reduction potentials. So remember when an um, when an atom when an atom gains an electron, so remember when an atom gains an electron, we call this a reduction, right? So we can tell if something's has a good redox potential for electrochemistry. So this will become more important in electrochemistry. What's actually the trend that predicts if something's redox active or acts as an oxidizing agent. It has to do with its redox potential. So with high oxidation, an element or atom that has a relatively high electron affinity will be a good oxidizing agent. So it wants to be reduced. Okay, so these processes are related to reduction. So it's the energy change associated with gaining an electron, right? So the halogens are particularly good at that, and that's why they have good. Some of these atoms like iodine, chlorine, fluorine, they're involved in electrochemistry processes, and they have high electron affinities and electric reduction potentials in electrochemistry. So that's why they're kind of related here. Okay, but the trend is not really explained in great detail, so we can't really explain it based on the principles we learned in this class fully. Okay, so you see here, there's definitely a trend here. You're going to increase affinity as you move up the periodic table, just like ionization energy. And it's going to increase as you go from left to right. So that's okay, right? So we kind of expected that based on the ability for an atom to pull electrons to itself to get a negative charge. We expect that trend. And we see in this table here with some tabulated values, we see that as we go up the periodic table, we get more negative. And then as we go across the periodic table, we get more negative as well. And then going down the periodic table, we tend to get less negative in some elements, but then for some columns, it tends to go up and down. Okay. So like, what's a good, like if you see in row 5, column 5 here, it starts at -51 for vanadium, but then it goes more negative when we go to niobium, and then I think that's tantalum, -31. So the trend's not really, it can't be explained very well, going from group to group, but in general we say. Electron affinity increases, meaning more energy is released as we go up a column and to the right of the periodic table. Okay, but don't worry too much about explaining the trend. Just kind of understand what the numbers mean. The more negative you are, the more energy you release, so the more favorable the process is. And then the less energy you release, if you need to put in energy to gain an electron, it's not going to be a very favorable process. And looking at these numbers, only a few elements break even across 0, and most of them have negative values. Okay, the noble gases don't have values at all, and that's because they have no need for gaining an electron. It's going to be energetically costly to do that because they're already at a stable electron configuration, so they don't want any more electrons. But things like fluorine, chlorine, bromine, iodine, they have the highest, and that's because they need only one more electron to get an octet. So that process is going to be very favorable. Same with hydrogen, only needs one electron, so it has a relatively negative electron affinity, but not so much as the halogens. Okay. All right, so let's move on here. Okay, so let's move down to now let's start talking about the new material here, Chapter 9, Lewis structures and determining molecular shapes. So you took chemistry in high school, or you took Chem 300. You should have encountered doing this. So this may be a review, but we're going to start from the beginning and then go into a lot more different shapes for some compounds, past the ones you probably learned previously, and then we'll learn how to draw these structures. Okay. All right, so Lewis dot symbols, they're convenient representations of an atom and atom's valence electrons. So in chemistry, we don't really, depending on what kind of chemistry you study, usually we don't care about the core electrons of an atom, generally because they don't do anything unless you disturb it. So what we're interested in is basically the valence electrons, or the electrons that are involved in chemical bonding or chemical reactions. Okay, so when we draw Lewis dot symbols, they're convenient ways to draw valence electrons of an element, and it's a neat way to keep track of these number of valence electrons during bond formation. So how we draw these symbols is we have a chemical symbol. And then, if you heard of electron dot symbols, they're basically, we put dots around the element for each valence electron that they have. Okay? All right. So let's think about silicon. Let's do this exercise here. Now that we've learned about these Lewis dot symbols, so silicon. So, the key to figuring out how many valence electrons each element has is to go to their group number. So if we go to silicon, we see it's in the same group as carbon. So it's in group 4A. So a little secret is that if you have the periodic table and you see what group it is, it'll tell you that it has that number of valence electrons. The group number equals the number of valence electrons. So for silicon, we have 4 valence electrons. So this means there are 4 valence electrons in the highest occupied energy level. Okay, so for silicon, we would draw something like this. So for drawing 4 valence electrons in the Lewis dot structure, we simply draw electrons around silicon until there's electrons occupied in all 4 quadrants around silicon. And then if there's more than 4 electrons, then we start pairing electrons. And that kind of happens, remember there's one s orbital, so the s orbital here, and 3 p orbitals. So since they're of the, well, technically speaking, they're not of the same energy, but we just consider that they are. So that's why we draw 4 electrons around it. Okay, but no, the reason why we draw 4 electrons, because in any principal energy level, except for 1, there's always going to be 4 orbitals in the highest occupied energy level. So for valence electrons, we only consider the s and p electrons. And that's because typically they're the highest energy level, right? Because if you go to 3s and 3p, usually the d orbital is not filled yet. So if only 3s and 3p are filled, you only count those. And then when you go up to 4s, the 4 energy level, usually it's 4s, then 4p, because then 4d gets filled later. So that's why we only consider the s and p orbitals. Okay, all right. But what about transition metals? Well, we look at manganese, right? Manganese, group 7b. If we look at that group 7b, so it has 7 valence electrons. So you may be asking, oh, but why do we consider these d electrons? Well, so there's a little trick here. So for transition metals, so let's just say for transition metals, okay, we consider d orbitals, or let's just say d electrons, so electrons in the d orbital. If the subshell isn't filled. Okay, so remember when we said like, oh, okay, the D and F subshells, right? They're typically higher in energy than their like their S and P counterparts. That's only if they're unfilled. When they're filled, the electrons, they populate those orbitals, and once they do, they bring it to a lower energy state because it's attraction to the nucleus. More electrons in those orbitals, so more attraction to the nucleus. And so only when these orbitals are filled, D and F, when they're completely filled, they're of lower energy. So, for example, when the D orbital gets filled, it's actually it's lower in energy than the 4s and 4p. So that's why we don't count them unless they're not filled. So for transition metals, we only consider d electrons if the subshell isn't filled, and that's usually only for transition metals because those are the only elements that'll have an unfilled d shell or f shell. Yeah. So usually we don't consider the d electrons unless the subshell isn't filled, and that's why manganese has 7 valence electrons, and that kind of makes sense, right? Because manganese, we seem to have like +2, +4, +6. So to be able to have +6, it must have more than 6 valence electrons. In this case, we look at the group number and we can see why it has such it has a variety of oxidation states. All right, so if we draw manganese here, put the electron around manganese. So we have 4. Then we start pairing electrons. 5, 6, 7. Okay. So there we go. We have 7 valence electrons for manganese. All right. All right. How about antimony? So antimony is in group 5A. So if it's in group 5A, we look at the group number and we see it's only 5, so 5 valence electrons. And what this means is that when we have 5 valence electrons, we only need 3 more electrons to gain an octet and be a happy, complete shell of electrons, which makes our identity as a compound more stable. So that's kind of how it reacts in nature. So in antimony, we will have 5 electrons. 1, 2, 3, 4, and then we just pair 1 electrons antimony. And we see here that antimony in this case will want to get 3 more electrons to be stable. So antimony usually forms 3 bonds with its compounds, but it can form more. It's not limited to 3, and that's because it has d orbitals that are available. Same with manganese. Metals typically don't bond like non-metals do, but it can form more than 4 bonds. And we'll talk more about that when we start drawing some compounds. Okay? All right, how about lead? So Pb is lead, based on the old name for this compound. That's why Pb is lead. It's in group 4A. And since it's in the same group as silicon, it has 4 valence electrons as well. Okay. So some common oxidation states, as you saw in one of the quizzes, is lead is 4+. So that kind of tells us Lead can have 4 valence electrons and lose 4 valence electrons to reach the +4 state. Okay, so that's how we draw Lewis dot symbols. Something we may see in the future, but this is going to kind of lead us into talking about drawing Lewis structures using lines and drawing structures, drawing the Lewis structure for a compound when we're given its chemical formula. Okay, so that will be okay. So we'll take a break here. So that will be the first part of this lecture. I'll see everyone in the second one in the next video. All right, bye bye.